Hi, everyone. My name is Shubham Rastogi. I'm a compiler engineer at Apple working on debug information. And today I want to talk about representing debug information in llvm-cas. So the agenda for today is going to be talking about caching builds efficiently using a content addressable storage, or CAS. Specifically, I want to talk about how to make DWARF debug information more cacheable. So let's first go over the current problems with debug information. So debug information is the bulk of an object file's content. On the right, there's a graph where we can see that I have built all of LVM and gathered the size of the object files. The bar graph on the right is a build without optimizations and without debug info, and the bar graph on the left is without optimizations but with full debug info. And you can see that without debug info, the size of all the object files is about 1/10 of the size with full debug information. So we can say that debug info accounts for about 90% of an object file's content. Debug info is also redundant. That is to say that there is a lot of the same information stored in multiple object files. This usually happens because of redundancies due to header file inclusions, right? Where each translation unit gets a copy of a header file's content in the debug info sections. So let's talk a little about the CAS object store. So a CAS object store where we store CAS objects, the object addresses or CAS IDs are a hash of the contents in the CAS objects. There is a one-to-one mapping between the content and the CAS ID assigned to the content, and the CAS ID is immutable. So once a CAS ID is assigned to certain data, that's fixed. If the data is changed, the CAS ID associated with it also changes. This is important because redundant data doesn't get stored multiple times. It gets stored only once. There's only one copy of redundant data, so we get what we call deduplication. Let's look at representation of content in the CAS. So content in the CAS is represented as a directed acyclic graph of CAS objects, as we can see in the diagram on the right. Each CAS object has some data and a list of references to other CAS objects, as we can see. Let's explain deduplication a little bit more in detail. So here we have two CAS objects, foo and baz. They both have a reference to a CAS object bar. Since the CAS object bar has certain data that's not different for foo or baz, we do not store any redundant copies, right? So both foo and baz should not have their own copy of bar, but both of them should have a reference to one CAS object that represents the data bar. And this is what we mean when we say deduplication. So we don't store redundant data in the CAS. So why should we use a CAS? We want to use a CAS to create a build cache comparable to something like ccache. Ccache's granularity is at an object file level. We want to split object files into multiple CAS objects for more finer grained caching. I would like to direct everyone to the talk that our team gave last year. This talk was by Stephen and Ben about using a content addressable storage in Clang for caching computations and eliminating redundancy. I would also like to point to the RFC we put up on LVM Discourse about the llvm-cas library that we've proposed, if anybody wants to check it out. Let's look at what a workflow, like current build workflow versus a CAS build workflow looks like. So currently you have a source file, you pass it to the compiler, at some point it gets to the LVM backend, and you can use the LVM backend to generate textual assembler, a DWO file, object file, etc. We have implemented a new object writer that we call a CAS object writer that allows us to generate either a CAS or object files. We can also materialize object files from the CAS. In fact, when we test the CAS to make sure it's correct, we materialize an object file from the CAS and we diff it with an object file generated by the LVM backend, and we make sure that they're exactly the same, so there is no discrepancy between the two. So let's look at what the contents of an object file look like in like some brief detail. So an object file contains multiple sections. For example, the Mako object file format groups sections into segments, such as the text segment, the data segment, the DWARF segment, etc. The debug information is part of the DWARF segment, and it can be further divided into multiple sections such as debug abbreviation section, debug info section, debug line section, and so on. So we will now that we've understood a little about the problem space, we can discuss how to make DWARF debug info more CAS friendly, because we want to use the CAS paradigm to reduce debug info size. So let's look at the debug string section first. Here's a simple example. Here we have two CPP files, a.cpp and b.cpp. They both have one function in them, nothing too complicated here. When we compile both CPP files down to their object files with debug information and dump out the debug string section using a tool like DWARF dump, we will see something like this. The strings in the debug string section are stored one after the other with the offset of the string in the section referenced in other sections. We can see that both object files have copies of redundant strings. So for example, the compiler version is present in both object files, so you're storing redundant information. You can also see that some redundant information may not have the same offset in different translation units. The offset is not guaranteed to be the same across translation units, like the string that represents the data type int here. So how would we represent the debug string section naively in the CAS? So one way to do it would be something like this. We have a CAS object that represents the debug string section. It has a reference to another CAS object that contains the strings in the debug string section. And we can see that there is no deduplication because the contents of the debug string section in both translation units is different. So there is no deduplication, they're different. So how do we store the debug string section more efficiently in the CAS? Well, one idea would be to create one CAS object per string. This way, redundant strings will have the same CAS ID, and therefore they will deduplicate. We need to be careful, however, CAS references are not free. They're 8 bytes. So once again, we can see what we had as a naive implementation. This is what it looked like. We can transform that into something like this, where now each string gets its own CAS object. And because that happens and deduplication should occur, we will actually see the CAS look like this. So you can see that now that the CAS representation for A.0 and B.0 do not have their own copies of the compiler version or the string int. They have a reference to a CAS object that represents that string. So here we have achieved deduplication because we do not store those strings multiple times. So to evaluate this methodology and make sure that this actually does give us some space savings, we wanted to simulate incremental builds, because that can give us that is a good evaluation methodology to see whether the CAS is helpful for space savings. And to simulate incremental builds, we took 10 commits of llvm project from 10 consecutive days at the start of every day. We built all of llvm with the resulting object files being ingested into the same CAS. So when we plot that out, this graph contains just the size of the debug string section. In blue, we have the size of the CAS with just the debug string section, where we create one CAS object per debug string section. And in green, we have the size of the CAS, where we create one CAS object per string in the debug string section. So because of deduplication, we get a much smaller size. You can see that the size of the CAS over 10 builds is significantly smaller, but the bigger thing is that the rate of growth of the CAS is also much smaller. You can see and that is what we are after, because incremental builds don't change a lot of stuff. So the CAS should help us. If we deduplicate well, then that means that we don't store stuff that did not change across builds. So this is how we store the debug string section efficiently in the CAS. Let's look at the debug line section next. So once again, to understand the debug line section, let's look at a simple example. Here we have two CPP files, a.cpp and b.cpp, and they both include a header file, foo.h. So what does the debug line section look like? Well, the debug line section contains a line table, where the line table maps source code addresses to source line numbers. The mappings are compressed into opcodes to a state machine, which is used to expand into the line table by the debugger. So if we compile both CPP files down to the respective object files and dump the debug line section using a tool like DWARF dump, we will see something like this. This is the line table representation when we expand the raw bytes stored in the debug line section, so via the state machine. At the top of the debug line section, we have a line table header that I have not shown because it's kind of verbose. But this part does not deduplicate. The reason it does not deduplicate is because it contains, amongst other things, the size of the debug line section, and that is not going to be the same for different translation units. Here I have marked the line table contribution for the function foo in both debug line sections, because that's what we're interested in. That is something that we want to see deduplicate. If we zoom into we'll see something like this. This is the raw encoding that is stored in the debug line section, which is then expanded by the line table state machine by the debugger. At the top here, we can see there's an opcode called DWLNS set file. This opcode represents a file number from a list of files included in that translation unit. And because the list of files for a translation unit are not guaranteed to be in the same order, this number does not deduplicate across translation units for the same header file. Here we have another opcode called the DWLNE set address, and this represents a relocatable address that is resolved at link time. So once again, it is not something that will deduplicate across translation units, and something that we need to handle. So if we want to store the debug line section efficiently in the CAS, we can take an approach where we split the line table so that every function's contribution to the line table is somehow distinguishable. The solution we came up with is to emit what we call an end sequence opcode after every function. And the end sequence opcode is a special opcode that usually denotes the end of a line table. But here we can use it to denote the end of a function's contribution to the line table. And all it does is reset the state machine to a default state. So that's perfectly fine. We can then create one CAS object per function because we have a marker signifying the end of a line table and a function's contribution to the line table and the start of the next function's contribution to the line table, right? We know the line table header will not deduplicate, so we can store that in a different CAS object that we don't expect to deduplicate, that I'm calling distinct data. We also need to store the file numbers and relocation add-ins in the distinct data CAS object block because we know that they won't deduplicate as well. I would also like to note that CAS references are ordered, so we can guarantee that the line table will be rebuilt exactly the same as it was in the original object file when we materialize the object file from the CAS. So a optimized representation of the debug line section in the CAS would look like something like this. We can see once again we have a CAS object in green that represents the debug line section. We have the first references to the distinct data CAS object block that contains the line table header, the relocation addresses, and the line numbers, which we know won't deduplicate. And then we can see that there is one CAS object block per function's contribution to the line table. And since A.O and B.O both both included foo.h and so should share the debug line information for the function foo, we once again see that we do not have copies for both of the CAS representations. There's only one copy for foo, and both A.O and B.O's CAS representation just get a reference to the same CAS object block. So once again, we've achieved deduplication. So when we plot the results out using the same evaluation methodology as discussed before, we see something like this. And once again, we can see that not only is the size over 10 builds a lot smaller, but the rate of growth of the CAS over 10 builds is smaller as well. And that is what we are mainly after. I would also like to note that compared to the debug string section, the order of magnitude of the size of this section is much smaller. Like the debug string section was in the order of 20 gigabytes or something, while this is more in the hundreds of megabyte range. So that also should inform us of what sections to prioritize when doing this kind of work. So now that we have understood how we can store the debug line section efficiently in the CAS. Let's look at the debug abbreviation and debug info sections next. We are talking about the debug abbreviation and info sections together because they have a very tight correlation. The debug abbreviation section contains the description of the metadata in the debug info section. And the debug info section contains information such as type information, function information, etc. Both sections can be divided into dies or debug information entries. An example of a die would be something like one type or one function roughly equals one die, roughly. So to represent that efficiently in the CAS, we went with an approach where we grouped dies into CAS objects via a specific heuristic that we used. So we would decide to put dies into a CAS object and create a new CAS object based on a type of die that we knew would not deduplicate and would have to be split off into its own CAS object. The debug abbreviation section has these things called abbreviation codes. These numbers do not deduplicate and are not stored. The good thing about them is that they can actually be generated when we serialize the object file. So we actually don't need to store them at all. So we get some space savings out of that as well. The debug info section has some specific metadata that does not deduplicate, such as relocation addresses, string pointers, offsets to strings in the debug string section, which are not guaranteed to be the same, right? And so those need to be stored in a CAS object that does not deduplicate. So once again, we store it in a CAS object block that we call distinct data. So once again, when we do this and look at the results over 10 builds, we see something like this. And once again, we can see that not only is the size over 10 builds smaller, but the rate of growth over 10 builds is also smaller. However, I would like to note that the results for these sections are not as impressive as the other ones. There is more work to be done here. So when you put it all together and look at it at the object file level, we can see something like this. So here I have a build of LVM, of 10 builds of LVM, once again, without optimizations and without any debug info. You can see that this is what it looks like, and I'm creating a raw CAS, where I'm creating one CAS object per object file. And it's only 3.6 gigabytes. When I add debug information into the mix, you can see that it balloons up to a huge size. It's actually 17 times bigger over 10 builds. And so this is why we focus so much work on debug info. Debug info is very big and causes the sizes to grow exponentially. But when we use a split CAS, where we create a CAS based on the optimizations we discussed before, we see something like this. I would also like to note that for all the other sections that we did not discuss today, we are creating one CAS object per fragment, where a fragment in Mako is anything between two labels. And once again, we can see that not only is the size over 10 builds smaller, it's almost a fourth of the size. The rate of growth over 10 builds is also smaller, which is once again what we're after. These are the results if we turn on optimizations. You can see that they're basically similar. So in conclusion, in this talk, we have showed how we can expose redundancies in debug information to make it more cacheable. And we've also shown that incremental builds benefit significantly from the CAS paradigm because the rate of growth goes down quite a lot. For future work, as I mentioned before, the debug info section definitely needs more work, and it can be further optimized. I'm confident we can get it down to something to hopefully look like the other sections. We also have not implemented any specific optimizations for the other debug information sections, such as the debug lock section, the debug ranges section, and so on. We do plan to contribute all the CAS work into upstream llvm.org. And once again, I just wanted to post the RFC to our llvm-cas library if anybody wants to check it out. And with that, I would like to thank everyone for listening and open the floor for any questions. Thank you very much.
If If I understood correctly, you said that this work currently does not look at DWO files or split dwarf at all. Is that correct?
Yeah, this is all for Mako. We've not done anything for anything that's not Mako.
Okay. So you have no plans to look at that in the future then?
Not at the current moment, no.
Okay, thank you.
So you talked about a couple problems where you have just sources of distinct data like file numbers and other kinds of references between dwarf records. And I was wondering if you had considered adding maybe new, I don't know the terminology, but like dwarf attributes, ways of having the reference that you're seeking to make just be a CAS ID, and then have that be so that would determinize like the content.
Yeah, I mean, DWARF is somewhat like that, right? Like there are references to other things. Like for example, as I mentioned, like the debug string section, you have the strings and then you actually reference offsets into a string. So that is something that we did, kind of think about. But it becomes more complicated. I think we had discussed it. We came up with a bunch of solutions, and I think this is still the best one that we could come up with at this moment. So there is more exploration to be done.
Hi, thanks for the talk. I have a question also on the string part. So you mentioned that the CAS reference is not free, so it's like 8 bytes. So if let's say int, do you still prefer 8 byte over 3 bytes? Yeah.
So for that case, like we did talk about doing something like that. We were thinking about storing small strings inline in the debug info section. So, but the problem with that is when you have to reconstruct the debug string section, you would have to store like a string table in the CAS to know what the offset of that smaller string was in the original object file, right? And that would be different. So then that comes with its own overhead. We have not explored that idea. That's definitely a thing on my try list, and we've talked about it, but as of this moment, we've not implemented it, and we still get like pretty significant, results. So it's something to try and see if it gives us any benefit. But considering that there's more work to be done in other sections, that's more low-hanging fruit that we can, kind of, and not as important that we can kind of, deal with later. But yeah, we have thought about it.
Yeah. That makes sense. Thanks.
Sorry, I'm new to this idea. But when you want to debug your program now, do you rematerialize all the dwarf, or does the debugger need to understand the CAS? And
so right now, you would have to rematerialize the object file. The whole point here is just to store the information efficiently. But why couldn't the debugger like actually learn and maybe even lazy load, right? Like maybe you could just load the debug info you need based on like if you have one function, maybe you just load that function's line table contribution rather than loading the whole debug line section, for example. Or if you want one type, you can lazy load. But that's not something we've looked at this moment. But it could be something you can build on this in the future. Yeah.
Hey, so putting an end sequence at the end of each function's contribution to debug line, I believe is something that happens automatically if you use -f function sections. So
I did not know that. So we just implemented our own flag. I called it CAS-friendly debug info, and and that's what it does. So I actually did not know that, and yeah, I just did that kind of.
Yeah, I don't know if Mako is able to take advantage of that.
I would love to try that actually. Yeah, so maybe then I can just throw that out and use that instead. Yeah, I had no idea, but yeah.
Okay.
Okay. Any last questions? All right. Thank you very much, Shubham.
Thank you so much.